Hi there, I hope you are well. Today's lesson will be Strength of Materials, Chapter 5, Stresses and Beams, Flexural Formula, Part 7. The flexural formula is sigma for flexural stress equals my over I, and the maximum stress equals mc over I or equals m over s, in which s equals I over c is called the section modulus with unit mm cubic. We went through this many times, and the review is done previously in many lectures. So just to remind you, with this section modulus for rectangular, triangular, circular, and hollow sections, for symmetrical section at the top and the unsymmetrical section in this figure. And for unsymmetrical sections, we can calculate the moment of inertia for the whole body or for the whole section using this equation. And d is the distance between neutral axis and the center of the part. So for each part there is d, just for your note. So the new things in this lecture is illustrative problem number 6, as shown in this slide. A rectangular beam 60 mm wide and 150 mm deep is simply supported over a span of 6 meters. If the beam is subjected to a central point load of 12 kN, find the maximum bending stress induced in the beam section. So it's a 6 meter wide span with a central point load of 12 kN and a section of 150 deep and 60 mm wide. So we can imagine the stress, flexural stress along the section of the beam like this one, or we can do it like this one as well. If we can draw it like this, it will be same. Okay, so the solution is begin with given width equals 60 mm and denoted as b, and depth d equals 150 mm. The span L equals 6000 mm and load W equals 12 kN or equals 12,000 Newton. So we know that the maximum bending moment at the center of a simply supported beam subjected to a central point load M equals WL over 4. So using this equation, WL over 4, the maximum moment will be 18 mega Newton meter. And section modulus of the rectangular section S equals BD square over 6 and equals 60 times 150 square over 6 equals 225 times 10 to the power 3 millimeter cubic. And so the maximum bending stress equals sigma max equals m over s and equals 18 times 10 to the power 6 over 225 times 10 to the power 3. The result of this equation equals 80 Newton per millimeter square, or the answer is 80 megapascal. It was a very simple illustrative problem for your notice. Illustrative problem number 7, as shown on this slide. A timber beam of a rectangular section supports a load of 20 kN uniformly distributed over a span of 3.6 meters. If the depth of the beam section is twice the width and maximum stress is not to exceed 7 megapascal, find the dimensions of the beam section. So the given is total load 20 kilonewton or equals 20,000 Newton. Span L equals 3.6 times 10 cubic millimeter, and depth of the beam section D equals 2B, and sigma max equals 7 megapascal or equals 7 Newton per millimeter square. So continue on this section of this slides. We know that section modulus of the rectangular section S equals BD square over 6. BD square over 6 equals B times 2B, as given that the depth twice the width. So B times 2B square over 6 equals 2B cubic over 3. And the maximum bending moment at the center of a simply supported beam subject to a uniformly distributed load is M equals WL square over 8. WL square over 8. You need to memorize this equation. Moment equals WL square over 8 for simple supported beam subject to a uniformly distributed load. So the maximum bending moment at the center equals WL square over 8. And equals W capital L over 8. W capital is 20 times 10,000, 10 to power 3, 10 cubic times 3.6 times 10 cubic over 8. This is the W kilonewton per meter as given here. Okay, the small one. And the total is as given here, sorry, 20 kilonewton WL. Okay, equals 9 times 10 to power 6 Newton millimeter. Let me double check if there is something missed here. Just to give you a hint about this equation, which is here, is WL square over 8 for W small w, which is kilonewton per meter distributed load. And here it's W, which is the total as given here. So if it's total W is 20, so the moment is 20 times L over 2. This is L over 2. So the moment will be 20 L or W, if the total W is here, W L over 2 as written here. Okay, so the maximum bending moment is 9 mega Newton meter. So jumping to the continue to cover the requirement of the illustrative problem 7 in this slide. So the maximum bending moment stress sigma sub max as given is not to exceed 7 megapascal equals M over S. So M is determined 9 mega over S, which is 2B square over 3 as calculated here. So in this equation, the only missing is variable is b, small is the width, so the width is equal to 125 millimeter, and d is twice the width as required by the example of this illustrative problem. So d equals to 250 millimeter is the final answer. In illustrative problem number 8, a hollow square section with outer and inner dimensions of 50 millimeter and 40 millimeter respectively is used as a cantilever of a span 1 meter. How much concentrated load can be applied at the free end of the cantilever if the maximum bending stress is not to exceed 35 megapascal? And this figure shown the cantilever with 1 meter span and the hollow rectangular section of the beam. Be careful and carefully follow the solution. Let W capital equals concentrated load that be applied at the free end of the cantilever. We know that moment of inertia of the hollow square section I equals B capital D capital cubic over 12 minus B small d small cubic over 12. So the outer dimension minus the inner, the outer modulus section minus the inner modulus section. So I equals 307.5 times 10 cubic millimeter to power 4, and modulus sections, I moment of inertia is the outer moment of inertia minus the inner moment of inertia, and modulus of sections is so return back to the recording of this lecture. So as we said, that moment of inertia of the hollow section is calculated by using the moment of inertia of the outer dimension minus moment of inertia of the inner dimension, as here. Okay, and modulus of section equals I over C. I is calculated here and C is 25 millimeter. So the S equals 12,300 millimeter cubic. Then, and the maximum bending moment at the fixed end of the cantilever subjected to a point load at the free end, M equals W, which is the total load times L, the span of the cantilever, and W times 1 times 10 cubic equals 1 times or 1000 W. So maximum bending stress sigma max sub max equals 35, which is given that the maximum bending stress is not exceed 35 megapascal. So 35 megapascal equals moment over S. The moment is 1000 W over S, which is 12,300. Then the only missing is W equals 430.5 Newton, the final answer. I hope these examples in order, and Thank you very much for listening to the lecture formula part 7.